Yes, so just a second. Yeah, hello everyone. Thank you for joining us today for Geo's talk. My name is Leonardo Muniz Pichel. I'm a research associate at Imperial College of London. And I'm going to introduce today's speaker, which is Apps. Gio is a research scientist with the AGL, the Applied Geodynamics Lab at the Bureau of Economic Geology, University of Texas at Austin. She holds an MA in Natural Science, Earth Sciences from the University of Cambridge and a PhD from the University of Liverpool. During her 32-year-long career in the oil and gas industry, she worked for Shell, BP, and BHP, and her career spanned basin analysis through exploration through production geophysics. She's a classic sedimentologist and a stratigrapher with expertise in deepwater reservoirs, salt-sediment interactions, and deepwater fold and thrust belts. Her current research interests focus on deepwater turbidite stratigraphy and reservoir variability in structurally active basins. Gillian is also a co-director of Appeel Geosciences, and she teaches field classes in Haute Provence in France. Gillian, thank you for joining us. It's a huge honor and delight to have you here. Thank you for accepting to give this talk, and and presenting on such an exciting topic. It's a very interesting subject. And that's it. I'll leave it up to you now. Thank you. Cheers.
Thank you, Leo. Thank you for that introduction. So the talk is going to be split into two parts, and the first part is technical and obviously takes up the majority of the time. And it covers the research I'm actively engaged in with my colleagues at the University of Texas in Austin, and with Dr. Andy Pullum, who is an independent consultant. And at the end of this technical talk, I'm honoring a request from Rochelle to briefly share my own reflections on the question of gender and the broader topic of diversity. I've lived in many parts of the world, the green circles here on the map, over my almost 40-year career, and I would say that cultural and economic heritage are as important as gender and race. In all walks of life, diversity enriches the individual and the organization, be it university or company, and society we live in. And the statistics are blatantly clear. Diverse organizations are demonstrably more successful, and interestingly enough, they are also safer. So for those of you who do not know me, I'm a geoscientist who started her career as a geophysicist and then structural geologist with Shell in the North Sea. And since then, I've worked in a number of tectonically active areas, here in red, for BP, BHP, and ultimately returning to BP. And as Leo said, ranging in scale from basin scale play fairway analysis to core description for reservoir modeling. Always at the interface between sedimentology, stratigraphy, and structure. And now I'm at the University of Texas in Austin, working with the Applied Geodynamics Laboratory team at the Bureau of Economic Geology. Rocks remain at the heart of everything I do. I use geophysical data, primarily seismic and well logs, but core and outcrop calibrate my thinking. And I'm about to give a presentation on the very largest scale phenomenon I've yet worked with, and yet it appears to account for some of the very smallest observations I've made in the last decade. And finally, I cannot compete with Zoe Cumberpatch's pole dancing, but I do have the coolest refuge in my field area here in Haute Provence that's built into a chevron fold. So the core of the technical talk is based on one I actually gave at GCS's EPM last December in Houston. And I'd really like to acknowledge my co-authors at this stage, Andy Pullum, Tim Dooley, and Alex Bump. And Tim Dooley and Alex both work at the BEG with me. And so why do we care about this subject that I'm going to talk about? Well, good science is based on observation, as we all know, but good prediction requires a great deal more than that. It requires an understanding of the mechanisms at work behind the observations we make. And predictive models for salt tectonics and salt-sediment interaction are important in many hydrocarbon provinces. The timing of salt tectonic events relative to sediment flux controls trap, hydrocarbon maturation, and migration. and even seal effectiveness via fluid pressure in deformed and often undercompacted sediment, where and when the thickest reservoirs are developed and even the best quality reservoirs. And today I'm going to look at this mechanism which drives much of what matters to us today, both as explorers in conventional and unconventional plays, and possibly even carbon storage. And it's one that has significant predictive potential, a driver that could account for a number of unexplained observations and provide a linking mechanism between two apparently unrelated phenomena, step changes in salt tectonic behavior and the very existence of large-scale basin floor fans detached from the shelf margin. So that mechanism is mantle-driven dynamic topography. And this diagram, the geoid here, represents the effect of the Earth's gravitational field, and it includes many factors, for example, crustal density. But a significant component of the long wavelength gravity field reflects mantle circulation, with positive gravity anomalies generated where the crust is warped down, positive anomalies where the, where the mantle plume distorts the surface topography upwards here in red, and negative anomalies generated where the crust is warped down above downwelling mantle in blue. So circulation in the mantle occurs at many different levels, well, two principally, and not all the cells penetrate deep into the mantle like the major hotspots. And the circulation patterns change through time. Therefore, not all upwellings are coincident with deeper seated hotspots. They may coincide at some points in space and time, but not necessarily. So for those of you who, like me, need a little revision or would appreciate a refresher on the Earth's structure, the Earth is divided into crust, mantle, and core based on composition. However, the equally important division is based on mechanical properties, and that is lithosphere, asthenosphere, and mesosphere. And the outer core boundary is the same in both cases. The lithosphere is solid, strong, and brittle, and it includes the upper part of the mantle. And it's the movement of the lithosphere that makes plate tectonics. The asthenosphere is still solid, but it's significantly weaker and relatively low viscosity than the mantle beneath, which is much, much stiffer. So the important consequence of the asthenosphere's weakness for our purposes is that the weak asthenosphere is the layer in which much of the mantle flow occurs. The hotspots are deeper seated and longer lasting, probably in the order of hundreds of millions of years. But the upper mantle circulation cells are shorter lived. So let's focus on the upper mantle circulation patterns for a moment. They vary spatially and through time, from symmetric to asymmetric configuration, with potentially multiple sources of heat establishing an extensive channel of hot, buoyant, low viscosity mantle near the surface, as shown here by Tobias Hoink. The most recent research, coming from Fred Richards' PhD under Nicky White at Cambridge University, would suggest that very low viscosity channels, approximately 100 to 150 kilometers thick, exist in the upper 300 kilometers of asthenosphere and are largely responsible for most of the Earth's dynamic topography. And the transition from hot to cold downwarp may actually be quite abrupt, with implications for surface gradient at that transition. In addition, the downwarps could be smaller and higher relief, while the uplifted areas may be very broad, as suggested by Hoink here. And I'll come back to that later in the talk. A figure from Richard's paper shows that at present day, the seismic velocity variations that are a proxy for mantle flow are spatially very variable. So the western flank of the Atlantic here has broad asymmetric patterns of upwarp and downwarp, whereas the eastern flank has a spatially higher frequency of much more symmetrical patterns. Madison East at the University of Sydney has demonstrated very recently that mantle circulation has also dramatically changed through time, with the whole mantle overturn, I'm going to repeat that just so you can see it, alternating with times when upper flow in the upper mantle dominates. So Mark Hoggard did this beautiful map in 2016, which basically shows the dynamic topography across the whole globe. And he established at present day that the peak amplitudes of the upper flow mantle circulation are in the order of 1 kilometre, with wavelengths of approximately 1,000 kilometres. And that is really important. These are huge scale spatial effects, and they produce very low slopes, but they're increased over a very large area indeed. And the dynamic topography signals evolve over the 1 to 10 million year timescale. And I'd like to draw attention to this particular timescale because that is the order of third order sequences as defined by Vail and his colleagues at Exxon. So the method used to calculate the component of surface topography due to mantle circulation is very easily demonstrated in the oceans at present day. The water-loaded depth of the oceanic crust, removing the effect of sediment loading, minus the predicted depth calculated from the age of the oceanic crust, which you derive from magnetic stripes, gives a residual topography, and that residual is the mantle-driven dynamic topography. And these seismic lines here show examples of both positive and negative anomalies relative to the age as predicted by a Dan Mackenzie style cooling curve of the age of oceanic crust. Okay, on the continents, however, establishing the component of topography generated by dynamic topography is much more challenging. There are so many factors involved in creating elevation, crustal thickness, density, etc. However, let's take the Colorado Plateau as an example. Wide-angle surveys and receiver function analysis of very far-traveled natural seismic waves have demonstrated that the crust beneath the Colorado Plateau is thinner than or equal to the crust beneath the Great Plains. And yet, the Colorado Plateau is present day elevated a mile above sea level. The region is associated with a long wavelength free air gravity anomaly, and tomographic models suggest the region is supported by upwelling hotter mantle. The timing of the uplift may be constrained a number of different ways, but the most complete record is preserved in long river profiles. And Gareth Roberts' paper was a real breakthrough in 2012, where he showed that by inverting, he could invert the uplift history from the fluvial Nick Point migration. And the longest rivers preserve the uplift history all the way back to the Cretaceous, the Upper Cretaceous. And I would encourage you, if you're interested in this methodology, to follow up with Gareth Roberts, who is now a professor at Imperial College in London, for more information on the methodology and the mathematics behind the analysis. So the effect of dynamic topography on surface elevation is one thing. However, the slope of the basement and all subsurface layers beneath the surface is enhanced by erosion where the dynamic uplift is onshore and by sediment loading in regions of downwalk. So a positive feedback is established, increasing that basement gradient and all other subsurface gradients between the source of sediment and the sink for sediment over time. And I want to look at this effect on two continental margins, each with paired uplift onshore and downwalk offshore, Angola and the Gulf of Mexico. And first, I'm going to look at the effect on the salt tectonics, and then I'm going to look at the response of the depositional systems. So on the response of salt, we're going to look at slope controlling the rates of salt movement in Kwanzaa, and then we're going to look at where and when to expect extension and compression in the Gulf of Mexico. So this west-east cross-section through the Kwanza passive margin, offshore Angola, shows truncation of all the pre-Miocene strata, here on the shelf, and that continues into the onshore. Offshore, we have a series of extensional growth faults in the slope section that record gravity-driven tectonic response to loading of the salt and the tilting of the margin. The growth fault history was documented by Mike Hudek and Martin Jackson in 2 papers, and they demonstrated that although the Miocene uplift was only a few hundred meters on the shelf, the rate of downslope translation during that time increased from 300 to 3,200 meters per million years. So first, let's deal with why. Well, salt, which is the substrate for this gravity-driven system, is a viscous fluid, and therefore the strain rate is directly proportional to the stress. Increase the gradient and you increase the stress experienced by the sediment wedge undergoing gravity failure. So what caused that increase in that translation rate? What tilted the margin? Well, at the time Martin Jackson and Mike Hudek were writing, they could find no tectonic event to account for the uplift. And since those 2 papers, a number of people have actually attempted to explain the uplift in terms of plate tectonics, and markedly Michel Giraud, and do apologize if I'm pronouncing his name wrong, I'm sure it's probably Guiro, talked about rift shoulder uplift at a transfer in the fault system at the Atlantic margin here. But as far as I can see, the timing is wrong, because the Cretaceous is when the rift history is at its most active. And this is Miocene, where we see all that downslope translation. So it took until 2014 for Jonathan Paul to actually map the present day dynamic topography supported by mantle upwellings and downwarps over the entire African continent. And Mark Hoggard's map in 2016 shows a corresponding downwarp offshore of the BA Dome onshore. And Jonathan Paul also looked at the timing of the uplift on the BA Dome. And what you see around the BA Dome is a radial drainage pattern, which is again a bit of a dead giveaway that this is something not related to plate tectonics per se. And what he was able to demonstrate is, through his inversion of the river profiles, a very rapid mid-Miocene rise in the rate of uplift of the BA Dome. That is coincident with that increased rate of downslope translation picked up by Mike Hudek and Martin Jackson in those growth faults. So I think we have a reasonably good explanation for the slope increase and the change in salt response on the Angola margin. So in that case, we had a tilt of probably a little greater than 0.5 degrees from source to sink. So now we're going to flip the symmetry and go to another passive margin where the sediment is deposited on salt, very active salt, and that's the Gulf of Mexico. And we have fluvial incision in the hinterland onshore, and again, the slope increase is about likely to have been 0.5 degrees or so, with that increasing into the basement because of erosion and sedimentation in the offshore. So present day, right, the upwarp onshore is the Colorado Plateau, and Gareth Roberts established the uplift history with 2 distinct phases of rapid uplift, one at the Cretaceous-Paleocene boundary and the other through the Oligocene and well into the Miocene. And these 2 phases of uplift are independently supported by fission track data and other geomorphological evidence. And interestingly, Mark Hoggard shows there is a negative downwarp present day centered in the deepwater Gulf of Mexico. An interesting side effect of this is that there is no abyssal plain in the Gulf of Mexico. It's lower continental rise all the way to the center and then back up to Mexico, which has big implications for sediment transport into the deep water. So the first phase of dynamic uplift in the Colorado Plateau is coincident with the Laramide orogeny that affects a much broader area. Ron Blakey's maps show that the Upper Cretaceous Fallen Basin to the severe orogeny is uplifted above sea level over the entire plateau area, and two major river drainage systems are established during the Paleocene, one to the north to the Boreal Ocean and one to the south into the Gulf of Mexico. And it's this system we're going to focus on today, later. But what happens offshore? Well, the first thing to note are the very large-scale gravity failure systems, routing down to the Luan Salt and also onto a Mesozoic age canopy. Large extensional gaps open up near the shelf edge, and they're filled with Paleocene and Eocene sediment, here referred to as the Wilcox depot trough in Carl Feduk's and Mark Rowan's paper. And the Wilcox is a very important reservoir system for the hydrocarbons in the Gulf. Time equivalent, we see compressional folds developed here in the offshore area, right out at the limit of the Mesozoic allochthon. And the Cretaceous, Upper Cretaceous strata are involved in those folds, and the paleotopography is filled with Paleocene sediment. At this time too, areas like this and this are inflated above thick salt. In other words, both the salt and the sediment were moving whole scale downslope. And that has big implications for the paleoslope profile during the Paleocene, with these areas of inflation producing perched, flatter areas before going on down towards the center of the Gulf of Mexico. Moving on to the Miocene and the second phase of rapid uplift, the first thing to note is the similarity with the Kwanzaa section. Erosion of all the pre-Miocene strata, and it's beautifully illustrated in this subcrop map on the Texas onshore area, and it continues into the offshore area, and what you see too are the growth strata of, well, the beginning of it is in the Oligocene, and then certainly through into the Miocene. And this cross-section was part of a paper by Tim Dooley and his co-authors at the BEG. Okie doke. So if we go to what Tim spoke about primarily in this paper in 2013, are the experiments he ran to show what happens in his sandbox models when you create a situation like this. And so let's look first on the top here in the maps B and C, where what it shows is the normal prograding margin, and what you get is up-dip extension at the top of the slope, matched with down-dip compression and shortening at the base of slope. And that's normal, that's a classic Coulomb wedge, with the center of the wedge being effectively translated. What happened then was he tilted the entire rig, which is no mean feat, I can assure you, and scraped off the sediment into an unconformity that mimics that we see. And what you see is that the extension stepped backwards, major extension on the exhumed shelf, not just at the shelf break, but also you have a spread of the compression back up the slope towards the shelf break. And in addition, he showed inflation of the salt in that down dip area. Let's go on to another experiment he ran, which is to show what might well be going on, that we see contemporaneous, on the seismic, what we see is contemporaneous folding at depth, detaching on the deep salt, while on a shallower detachment, you get extension at the same time on the slope during this Miocene time. So what he was able to do was to create a situation, in this case not eroded, but he created a double detachment system and tilted the entire rig. The extension on the main deeper detachment stepped backwards, Meanwhile, the extension on the upper detachment carried on, underneath which you have compression, which is matching the extension of that stepped back system on the deeper salt. Very interesting indeed. So, the Gulf of Mexico, remind ourselves, salt is viscous. So where you have no dynamic topography, you have a situation that is much closer to equilibrium, with the failure being limited by the strength of the wedge, classic Coulomb wedge stuff, extension up dip, compression down dip where the salt ends. With active dynamic topography, it's far from equilibrium. The deformation is fast and the failure is limited by the viscous resistance of the salt detachment. Strain rate is proportional to the stress applied, and increasing the slope gradient increases the rate of deformation. Steeper parts move faster than the lower gradient portions, leading to the traffic jam effect, with compression migrating backwards up the slope in the same way as cars increasingly get involved in a traffic jam, up dip of the obstruction. So salt, I think we've demonstrated, does respond to transient dynamic topography. Because salt is viscous, strain rate is proportional to stress, and gravity-driven failure speeds up, and you get a change in the distribution of extension and compression in the deforming wedge. But as I've noted also, hinterland erosion and redistribution of the sediment load to ultra-deep water exacerbates the subsurface tilt. And so what are the consequences of this for the sediment supply? So in the second part of this, I'm going to look at the impact of dynamic topography, where we increase the gradient from source to sink, and another secondary effect for us in the sediment world, we see associated volcanism in the upwalk domain. The effect on the dynamic topography on sediment flux, slope stability, and reservoir quality. And I'm going to use the Gulf of Mexico, Paleogene and Middle Miocene as examples of this. Okay, so we've known a lot about Gulf of Mexico sediment sources for a very long time, but I think the dynamic topography uplift actually adds an extra component to this. So we know that all the uplifted plate tectonic areas add sediment into the Gulf of Mexico. But if you look at the Mississippi drainage area, particularly in the Miocene, it includes uplifted areas in the Appalachians, way away from the foreland of any of the Lauramide orogenic events going on the West Coast. And I think this is due to the effect that we were talking about earlier, that these areas of upwelling can be very, very broad areas of uplift over a huge, huge area in the upper mantle. And I think that almost certainly is what accounts for reactivation of the Appalachian source areas. Okay, so let's look at that first phase of dynamic topographic uplift at the Cretaceous-Paleocene boundary. Well, after a very short time gap, it changes, it produces a first order change in the Gulf of Mexico. Prior to the day this all gets going, sediment into the Gulf of Mexico is very limited. We get discrete times of clastic input, but for the majority of the time, all the clastic sediment is held up in that interior basin, which is the foreland to the severe orogeny. And what you get in the Gulf of Mexico is strongly aggradational and progradational carbonate margins, and then offshore carbonate pelagics and carbonate turbidites. At the Paleocene-Eocene boundary, it doesn't take long before the world changes. And from then on, the Gulf of Mexico is dominated by clastics as all the river systems establish themselves, draining the Colorado Plateau and reworking the entirety of the interior basin sediments. So initially they're held up in lacustrine basins in the Lauramide area, in those little contained basins up there, But very soon that system gets going and the sediment is shed directly into the deep water and we get our thickest reservoirs. In fact, the rate of sediment flux approaches that of the Pleistocene in the Paleocene. It's incredible how much sediment is translated directly into the deep water. Glenn Sharman's paper is a really good documenter of that, but it's also one of Bill Galloway's big topics. In phase 2, what happens? It's very, very interesting. So Oligocene to Miocene. What we see is that the nature of deep water feeder systems changes dramatically, and we cease to have discrete canyon feeders into the deep water. Instead, what we have is a series of massive shelf margin breakups, complexes. And what you see is that the shelf margin at periods of time is incredibly unstable, and it collapses lock, stock and barrel over very, very large areas indeed. So the early Miocene has a system that is 200 kilometers, 200 miles plus long, but the middle Miocene, if you add all this failure together, is a system that's about 400 miles long. So this cycle of shelf margin progradation, failure, healing with deeper water sediment, and then renewed progradation is one we see again and again and again right through this period of time. And what do these look like? What does this look like on seismic? Well, here's what you see. You see discrete failure blocks, and these, when you drill them, turn out to be deltaics and shelf sediments, above which you see an onlapping wedge of deeper water sediment, which onlaps up into the head wall of this large failure system. And it pinches out up dip. There are no up dip equivalents. There is not a transgressive systems tract that is time equivalent to this deeper water wedge. And then what you see is once that topography is healed, then the shelf progrades rapidly back over that system entirely. What do you see inside the bathyal wedge? Well, the majority of it is mud rocks, and they're generally overpressured and really difficult to drill. You also see thin and ratty turbidites, and it's dominated by agglutinated forams, which are basically forams that stick pieces of sand to their bodies to get rigidity, rather than using, and they're very, very common in carbonate-starved areas. So they're common in highly turbulent waters. So all in all, there's a big story going on here. And what I said to you earlier is we see progradation of a shelf margin, failure, healing, progradation, failure, healing, progradation, failure. And that cyclicity occurs all the way through the Miocene particularly. So what's going on? Well, this is a really lovely couple of diagrams by Andy Pulham to show what happens that's time equivalent to the bathyal wedge, which we were talking about earlier, in the shelf and the flex area. What do you see in the deep water? So this is a log from the Western Atwater Fold Belt area, and it shows that the major sands in both, well, in this case, the middle Miocene, occur at the same time as the bathyal wedge is developing. And that set of sands in here is coeval with the healing phase of the big shelf margin failure of the Pontchartrain in the middle Miocene. So the model is that what you get is a collapse of the shelf margin, presumably not a single event, but a series of very rapidly spaced events, producing megabeds of very big thickness and lateral extent. And those reservoirs are relatively poor quality, but they are reservoirs. Once that has happened, then the footwall of the head wall of that scar uplifts and the fluvial systems incise deeply into the head wall, and they establish a series of slope channels, and a far more organized system develops on top. And so what we see is that the upper parts of these reservoirs are much better quality, and they're more organized in terms of their fan lobe complex distribution. Finally, the reservoir quality. So this is the smallest effect of these very large dynamic topographic uplifts. What you can see on Gareth Roberts' diagram here is that the second phase of dynamic topography is associated with volcanics all over the Colorado Plateau. Now I have an example of one ash that we had looked at the University of Utah. It's the Hurlbut ash, and it's 3.6 million years old. And what we have in the deep water is a time equivalent redeposited sandstone, which is dominated by volcanics. The log signature is that of volcanic ash. And this map was compiled by Andy Pullen, who pretty much pioneered recognizing these ash flows in the Miocene. And we assume what happens is they do have a temporary storage in the fluvial systems, but that they choke the fluvial drainage completely and the shelf margin systems, and that they are reworked very rapidly into the deep water. Now that itself is tight, but the volcanics from this time period also contaminate most of the middle Miocene reservoirs. So the lower Miocene reservoirs are really clean. The middle Miocene reservoirs have this volcanic ash in. Okay, so coming back to the very first example I showed you, which is a paper by Dave Jeanette from Exxon at the time in 2000, talking about the Paleocene deep water detached fan systems that come through incised valleys but are not time equivalent to any shelf. Well, the contemporaneous event going on in the mantle was that the ice and plume was initiated, and Adrian Hartley and his colleagues again at Cambridge actually have mapped the uplift of this ancient buried landscape, and it's beautifully illustrated that you have incision at time equivalent to a lot of these detached deep water fans. So in conclusion, transient dynamic topography does account for some unexplained observations, and it has a dramatic and predictable effect. Step changes in salt tectonic processes and rates, and dramatic changes in sediment flux to continental margins, shelf margin stability, and deep water systems can all be related to this 1,000-kilometer scale gradient change across the entire source to sink system. And it's no surprise that changing the regional gradient, even by a relatively small amount, has a profound effect. And we've only recently begun to understand the full implications of dynamic topography, but it is mappable in space and over many areas through time. My own personal prejudice is that one of the most important drivers for second and third order classic sequence boundaries, and in the Gulf, I think we can make a really good case for this, that the mantle-driven dynamic topography is responsible for those sequence boundaries, and it's actually producing the slope needed to detach the deep water fans completely from their coeval shelf margin. In the Gulf too, we see it as a first order effect on the change from carbonate to clastic deposition of the Cretaceous-Paleocene boundary. So that is the end of the technical talk. And at this point, I think Rochelle might like to bring in technical questions, because I think the next stage will be a little different.
Yeah, so thank you so much for that, Jill. It was wonderful. Love your conclusions. There are just a few questions. So the first one is, actually there is a hi Frank and Jill from Julia Gale. And the next one is Eric Scott.
Oh, Eric, yes.
How does the Chicxulub impact fit into the deep mantle processes and the switch from predominantly carbonate to clastic sedimentation into the GOM? Can
Yes.
this relationship be applied to other basins that experienced significant asteroid impacts?
It is such a good question. It's really interesting, and Mike Hudek and I were discussing this the other day. It's not something I dare to make a direct link to, but it does seem to me, I doubt that a single meteorite would have a profound impact on the mantle circulation patterns, but I wouldn't like to say that the Chicxulub impact is the only meteor that hits the Earth at this time, because from what I've heard, there's at least one other massive one up in Siberia that would be time equivalent. So it's quite possible that the Earth actually sustained a number of meteorite hits within a very short space of time. And I know your work, Eric, particularly was absolutely critical to establishing the existence of a vast megabed of clastic material as the shelf collapsed completely all the way around the Gulf, presumably actually comprising both clastic and carbonate material in it. That was really, really groundbreaking work, and I think just the sheer drama of the Paleocene, Cretaceous-Paleocene boundary, I wouldn't like to say it didn't have an effect on the mantle, but I think somebody who works in mantle dynamics is probably going to have to be the person who makes a comment on that one. I think it's a good idea. And certainly we see all around the world, we see Paleocene and Eocene deep water sediments, a lot of them detached from their time equivalent basin margins.
Thank you for that. The next question is from Mark Rowan. He says, Jill, you show the effect of dynamic topography in the GOM in Wilcox and mid-Miocene times, but the Oligocene Frios system was also an enormous dump of sediment with massive localized failures. How does that fit into the story?
Yeah, absolutely, Mark. If you actually look at when that dynamic topography takes off, it's in the Oligocene. I mean, it's obviously going on even between the Wilcox and the Oligocene, but it starts to pick up in the Oligocene. And I actually totally agree with you. The Hackberry system and all its associated sediments, a lot of which we still have to account for in the deep water Gulf. And in fact, you're probably ahead of me on that one, because I've been out of the exploration world for long enough to not know whether we've seen a big enough wedge of the deep water sediment equivalent, but one would predict it would have exactly that effect, yes. So you can definitely map the failures as happened a very, very long time ago. And I would add the Oligocene into that, no problem. I just don't happen to have worked it.
Thank you. The next question is from Peter Clift. He says, I wonder if it's possible to differentiate faster erosion driven by plume-driven surface uplift or those caused by climate change.
Yes. Oh, it's so interesting you should say that. Peter, I'm totally with you. And in fact, of course, climate change in the Miocene is actually critically important to sediment flux to the Gulf as well. And let's be utterly honest, it's one of the biggest debates in Andy Pullum and I, because until I kind of got the dynamic topography bug, we would have both agreed that it was climate change that was driving a great deal of that Miocene response and the instability at the margin. But I do think they can be deep involved, and I think it's something that you, particularly Peter, would be a really good person to initiate a series of projects on, because you work at that scale and you have done in research for so long, and I would be delighted to collaborate.
This is from Leo. He says, hi Jill, thanks for the super interesting talk. Are you aware of other margins where mantle dynamic topography has significant impact on salt tectonics? Do you know any evidence for it on the Brazil side of the Atlantic margin as well?
Absolutely, Leo, and I would be more than happy to talk about it. I haven't got any maps on me now, but yes, I think it's critical and very important to new plays as well that we could talk about, and I'd be delighted to follow up with you on that, and I will.
The next
Yes,
question?
I mean, basically, talking of which, there are so many people now, so many research students, and Cambridge is leading, Cambridge University is leading a lot of that on this inverting, and obviously Imperial now that Gareth's there, on the inverting river profiles to get the history of uplift of the dynamic topography. And they have done Australia, they've done Mexico, they've done Brazil. Of course, I have to deconvolve what I learned through BP with what they've actually published, but they're definitely publishing a great deal of that over the years as we come through. Yeah.
Okay, great. The next question is from Connor O'Sullivan. He says, great talk, Jill. Thank you for sharing. Other than the models you showed in this talk, are there any other good diagnostic indicators for the influence of dynamic topography on rift basins?
A very good question, and I think I'm going to have a little think about that. Rifts becoming oceans, absolutely. Southern Atlantic being one of them. They're at the bottom end of the Sacktoss Basin. There's a massive dynamic topographic uplift at that closes off the lacustrine setting in that rift, that whole rift environment of the pre-salt. And it's, you know, we still see the volcanic activity associated with what becomes a transform system there. But at the time in the middle Cretaceous, it is huge. So yeah, it's an indirect answer to your question, and it's not very specific. But if you go back to some of that Madison's work from Sydney, she basically proposes that the breakup of Pangaea, which obviously is a whole bunch of rifting, is initiated by a storm overturn deep in in the core, which then causes circulation in the lower mantle as well, and causes some very large hotspots to set up. And they are then where the megacontinents rift. So take a look at that paper, which is referred to in here, and I can send you the link, but we can talk again about specific other examples you might wish to know about or think about.
Jill, we have about 7 or 8 more questions. Do you want to continue with those or go on to the last part of your talk?
If the people who put them wouldn't mind me seeing them in an email, I think we'd probably better move on because people would not want to hang around too long, I should think. So I'm delighted to answer any questions, but perhaps send them to me in email and I promise I will answer them. And if you have any kind of forum you want to put the answers on, then we can upload them later.
Sure, yeah. I'll copy and paste them for you as well from our end. Yeah. That's what we've been doing.
Oh, would you mind? That would be fantastic because I'm not sure I can find them again once I've logged on.
No, don't worry. I'll copy and paste them. So yeah, I'll let you continue with the last portion of your talk.
And thank you, everyone. I'm really appreciating the discussion, and I just want to encourage other people to actually get involved in the research. It's good fun. Okay, so now for something completely different, as Monty Python would say. And I'm using this as a transition slide because I think most women in the audience will have experienced something along these lines where an attribute in a man becomes something to use as a hammer against your female colleagues. Okay, so moving on. The business case for gender diversity is, I don't think it's debatable now. And a recent report in November 2019 by the Hampton-Alexander Review, it's called, and it was done for the Business, Energy and UK Strategy Department of the government. And they basically say that companies that have a team diversity, executive team this is, of 15 to a really diverse executive team, and that doesn't mean just one woman on the team, are 15 to 24% more likely to outperform their national industry median, which I think is a really telling figure. But in that same report, there are a couple of comments on how slow this change is basically taking place, and it's very easy for it to slide. And I think the professional institutes have an enormous responsibility and accountability to change the conversation and by changing the way their executive committees and their boards are actually made up. And I think without hammering on an old topic, I think looking at this year's executive committee and plenary committees with older generation white male dominating them is really not appropriate in this day and age. And although the Geological Society of London ended up with really quite a balanced gender representation, I was sad to see the nominations in 2021 being quite biased towards men again. So in industry, the challenge is not hiring, it's retention. And those of us in industry, in the energy industry, will recognize that in all the oil price downturns, it's the women who go preferentially, and that's happening again now. And it isn't always that they are asked to leave, it's often that they have already thought about in their flexible careers other options, and they choose to go. But the bottom line is it is difficult to keep women in the industry. And Graham Sparks, who in a personal communication with me in May, was the former head of diversity and inclusion for Shell. And he said, basically, the bottom line is you need to equip your women to succeed, but you also need to create an organization where men are willing to stand up and speak up against sexism. And part of the way of doing that is to assign very specific actions and accountabilities in leadership. Now that's okay in industry because behaviors are actually rewarded in industry. And so you can actually teach, recognize and reward the behaviors. You can assure that the job descriptions are appropriate for women who may need a little more flexibility in their lives. And you can reward performance that acknowledges diverse roles. But I think in academia, it seems to me that it's particularly difficult to do when the metrics of success are often the number of papers you publish and the research grants that you land, and that's it. So in a very personal way, I'd say that it's essential to develop a real resilience, the ability to bounce back and learn from your adversity, learn persistence, but also be willing to stand up for others, whatever your gender. But I'd like to also highlight and showcase something that Eleanor Snow, who is the National Manager for Youth Education Programs at the USGS, and I should have put her Twitter handle on here, but I can definitely forward it to any of you who are interested. But it's basically youth and education programs. So I think it's YEP. Anyway, USGS YEP. And they have many, many programs, but this one I just love the name of, and it's called the Raspberry Shake Project. And what they are doing is using the vast increase in citizen science to start with the native Hawaiian schools, where they give them Raspberry Pi computers, which are really simple and easy to program. And they can turn, the students turn these into geophones, and they're basically monitoring the seismic wave activity related to magma rise beneath the main volcano on Hawaii, on the island of Hawaii. And this is an example of not only engaging the youth, but also engaging the whole community. Because one of the things we find is that if you, you can engage the youth in STEM subjects, but if the community don't understand or don't see the role models that their children can actually become, then they don't encourage them to go on to do STEM subjects at school and STEM subjects in college. So engaging the whole community is very important, and providing a complete pipeline of opportunities. Economically challenged communities need to be supported financially at college, but also through the summer vacations in America with internships. And then, especially during COVID, work to create the entry-level jobs for graduating students. So it's a big job that's actually being undertaken in many countries now. So what I mentioned earlier on is that diverse organizations are safe organizations. And I think this little example, my own personal example, shows this rather well. And it's partly because organizations, in order to be safe, need to include all team members. So you require the involvement of the entire team to come up with a safe solution to any problem. Right, so Frank and I were posted to China, and this was back in the early 90s, in 94. And we were a completely new team with equal numbers of Chinese and largely British, UK BP employees. And the first thing they did was they sent us on a team building course, which was located very close to the Great Wall of China. And the most memorable exercise for me was one in which we were given the challenge of throwing an egg off the Great Wall of China, but protecting it with only the tools provided from cracking. And the tools were 6 sheets of white paper and a roll of sticky tape. And so the challenge was to create a protective environment for the egg, which was a raw egg, of course, to land. So what was absolutely fascinating was that the team was balanced between the nations, but it was also balanced with gender, and it was also a very broad representation of the disciplines involved. So we had geologists, engineers, and also administrators. And the team that was successful was actually Frank Peel's team, and he was able to recreate this little example here, and it's now hanging behind me in the office. But what they produced was a rigid framework, which is this pyramid here, created by rolling the paper, and that provided a framework that was able, and actually did break and crumple when it landed, but it took a lot of the shock. But then that shock was prevented from reaching the egg by these origami folded concertinaed elastic strength strands that connected to this little concertina area in the middle here, into which the egg sat. So in here sat our little raw egg, and then these elastic strength strands took up all the shock from the impact, and the egg came out intact. I think it's a really, really good example of cross-discipline, fully diverse team, better, safer solution. And so I'd like to end with just an acknowledgement of 2 people who I've consulted quite extensively on this to get the examples, Graham Sparks and Dr. Eleanor Snow. And I'd like to thank them very much, and open to any broader questions, if there are any, for me. Thank you.
Thank you, Jill. That was really wonderful. Would you like to finish any of your technical questions?
Yeah, if you like. Happy to.
It's okay. It's totally up to you.
Yeah. Because
okay,
people
so
can
this
now as they wish.
Okay, that sounds great. Okay, so this one is from Piotr. He says, Jill, do you think that dynamic topography effects could have influenced regional salt tectonics, etc., in epicontinental basins such as the Permian-Zechstein Basin in Europe?
Yes, I do. And actually, I don't have any experience of this, but I would be more than delighted to actually extend this research with anyone who is interested in working with me. But what I do know is they have a profound effect on unconventional reservoirs. It's why I brought it in, because a lot of us were struggling to understand the subsidence of some of the bigger interior basins, the subsidence histories of these huge basins that start off with an upwarping and erosion, and then over a very long period of time, that collapses back down and often goes on subsiding in the opposite direction. And yet they're underlain by no rift of any significance. So they can't be accounted for. The subsidence curves cannot be accounted for using a Dan-Mackenzie model, not even vaguely. So those huge interior basins are where I think dynamic topography is really important. And I was talking with actually Sean Evans about how interesting it would be on salt, because a lot of those interior basins start off with upwellings. So in other words, all the surface gradients are going in one direction and they end up going the other way. So if they aren't entirely compensated for by sediment, as a lot of the interior basins are, you might well see a reversal in the effect on the salt, which I think would be fascinating.
The next question is from Kate Giles. She says, "Hola Jill, do you think the Colorado Plateau uplift could extend back into the Triassic and account for the series of regional erosional surface across the plateau in the Triassic and Jurassic?"
Interesting. Presumably not the same one, Kate, because I think I'm going to have to, again, talk to people who understand mantle processes, particularly in that area. But what I'm understanding at the moment is that the reason the one we're talking about for the recent Colorado Plateau gets going is because of the change in the subduction angle of the Farallon plate, I believe, and it basically steepens up. So you actually get a circulation system in the upper mantle actually established, but that timing would be later. So I absolutely would say go seek, and a person who might actually know the answer to that question, and I don't know if he's online, but Alex Bump. So if he is, he has worked more in the Colorado Plateau than I have for sure, and partly because it was his PhD area, but he also spent a lot of time with Nicky White out there, and I'm sure he's thought about those earlier erosional surfaces. But my own opinion on very major regional, very extensive unconformities is go seek out the dynamic topography that's mantle driven, because it seems to me like the main mechanism for creating those super wide aerial extensive erosion surfaces. Yes.
Cool. This one's from Jonathan Brown. Does anyone have an opinion to explain why the Iceland plume has been so long-lived?
Again, I think it's got a great deal to do with the fact these are super hotspot overturns from much deeper in the mantle. And this actually relates to Kate's question as well. So if we go back to Madison East's paper this year with this breakup of Pangaea, then she calls upon these core storms to create these mega hotspots. So the hotspots are much longer lived. They are deeper seated and they involve very large scale, deep mantle overturns. And of course, Iceland is a major hotspot. So is Yellowstone is sat upon a very deep seated hotspot that has migrated a long way up the Snake River over time as America's moved over it. But so the upper mantle circulation is at times, like in the Colorado Plateau, coincident with the deeper seated hotspots, and at times it isn't. And again, on the Iceland one, go to Nicky White. Definitely, I would recommend you go to the Cambridge team for the length of duration of that Iceland plume. Have you got any comments on that, Frank? I see you moving into the frame.
Yeah, I would say the team that is really taking that question apart most is the team at the University of Sydney in Australia.
Yeah, that's what I said. That's Madison's team.
Yeah, so people like Madison and Savin Zahirovic have been looking at that question of what actually drives the initiation of plumes. Once they're initiated, they keep going for a long time. So plumes are different from the kind of mantle flow that Jill was talking about for most of this talk. They're, okay.
Yeah, yeah. So split the two. First slide, well, one of the first slides showed that, you know, you get these deep-seated circulation systems, but you also get the upper ones, and the upper ones are very transient. But Iceland is a deep-seated one. Yeah.
This next question is from admin. This might be someone from AAPG, but I'm not sure exactly. It says, hi Jill, what is the relationship between the uplift of salt movement and the seismicity response?
Ah, okay. So, well, two questions, two answers within there I can see. So the relationship of the uplift was to demonstrate that, initially, was to demonstrate that the Colorado Plateau is a high, not because the crust is thick, but because the crust is thin and supported by the mantle upwelling. So, or not because it's thin, but it is thin, and it is therefore supported by something else, which is a mantle upwelling. And that's the tomography part. But the seismic velocity, or the shear wave velocities actually demonstrate that the crust is very thin there. So that's one of the times I referred to seismicity. And the other, well, you get seismicity associated with volcanics, but I've got a feeling he was probably referring to the circulation systems. Yeah, okay. And if you want more details on seismic velocities and tomography and modeling the flow in the mantle, definitely Fred Richards' paper has got a good summary in his on the process of that tomographic inversion.
Great. Here's just a comment from Jean-Claude Ringenbach.
Oh,
he
hi,
says,
John.
Thanks, Gillian. Very nice talk. I will forward the YouTube link to my students. Warm regards to you and the guy with the bandana behind you.
The pirate. Thank you, Jean-Claude. And can we come out in the field with you next year? Because this year hasn't been possible.
And then we have one last question. This is from Nizar Ahmad. He says, excellent talk, Jill. What may the rule of overburden thickness on salt movement on a sloppy shelf? I'm not sure if that like a steep shelf, but he says sloppy shelf.
Okay. So could you repeat the beginning part of the question? Because what made what?
He says, what may the rule of overburden, so maybe what controls the overburden thickness on salt movement on the
controlling pressure, you think, or on the instability?
Controlling the instability.
Controlling the instability. I'm going to repeat the question back because there's a couple of interpretations of the question, but I'm thinking what he's asking is, how does the sediment load and the fact it's underpinned by salt affect the instability on the shelf? Is it? Do you think that's what he meant? Potentially?
Yeah, potentially, okay. Yeah.
Let's try that one, because actually, oh, this is something I'm really interested in. So in fact, one of the reasons the Miocene is so fascinating in the Gulf is because it's actually building out, trying to build a shelf margin onto a reasonably coherent set of shallow detachment canopies that are formed in what's called the flex trend, which is at the boundary between the upper slope and the shelf. And, well, observationally what you see is you see a whole bunch of diapirs that are angled down towards the basin. You also see counter-regional faults. And essentially, I can only say that in a counter-regional system like that, you're increasing the angle of the topographic slope in the upper slope area. If you're increasing the slope, you are making it less stable and more prone to gravitational collapse. So the propagation of those big failures is almost certainly enhanced by the fact you've got salt and reasonably coherent salt sheets underneath that advancing shelf margin. And it contrasts really markedly with Texas, where you get growth faults that are down to the basin. And I can't even begin to explain that difference, but that's a whole nother topic. But where you have the down to the basin faults with big growth faults, then obviously they are stabilizing the shelf margin. And you don't see these big failure complexes as you go further east. Interesting, isn't it? So that's one answer to a question that I might have misinterpreted, but I can only apologize.
Thank you for that. Oh, and our admin was Dr. Mohammed Gaharbi from Tanzania.
Oh, brilliant. Excellent.
Yeah.
Okay.
Yeah.
Oh, so
okay. And then, yeah. And then let's hear, we have Jonathan Brown just says, thanks, Jill, for giving insight for the big picture and an excellent presentation.
Oh, thank you. Thank you, everyone.
And that's the last one. So thank you so much for your time and for allowing us to go over a little bit. We really appreciate it. If anybody else has any other questions, please feel free to email Jill if you know her email, or you can forward your question to us, aapgsaltbasins@gmail.com, and we will forward it to Jill if you don't have her personal or work email.
Rochelle, thank you. Thank you, Leah, for the intro. I really appreciate this opportunity. It's been fun.
Yeah, thank you so much for being such a good leader and mentor in our field. We really appreciate it.
Thank you.
The last bit that I just wanted to remind everyone is our next webinar is on September 1st. And we have Karina Rodriguez from Searcher Seismic presenting. Her title will be Prospectivity Relations from Enhanced Salt Flank Imaging. So we go to, again, another completely different topic within salt that's based more on seismic. So thank you so much, Jill, and thank you everyone who could stay on a little bit longer. And I think that's it for today, unless you had any last comments or thoughts.
No, just thank you very much, and thanks everybody for all those questions. Thank you. Bye.
Thank you. Yep. See you in 2 weeks. Bye.